Hello everyone and good evening. Welcome to the OneClass channel. My name is Fejiro. I'm an honors Bachelor of Science graduate working towards medical school. So for this session we'll be going over some commonly asked chemistry questions at both the high school and the college levels. If you need some extra help with the homework or even tutoring, you can check out the links in the description below. And with that, we're going to begin this session. This is going to be longer than I typically do, so we have a little bit of nice background just sound, so that way it's a little bit more relaxing. So with that, let us begin. So as you can see here, our first question for the evening is, how do you convert meters cubed to centimeters cubed? So with that, in terms of these questions, right, we need to make sure that we understand how we get cubed. And in order to do that, we need to understand, specifically in this case, what's the relationship between them, starting at the base. So with that, right, 1 meter, right, is how many centimeters? So if you remember centi, that's 100. So it takes 100 centimeters to get to a meter. Now these are some things that you might have to just memorize, like the ones that are commonly used, like centi and milli specifically. Those are the ones that are really recurring and you'll see them quite often. So it's important to just memorize them and get familiar with them. So with that being said though, now that we have this, we have to cube this whole thing in order to get the centimeters cubed. So 1 meter cubed, as you know, 1 cubed is still just 1 cubed. I mean, well, it's still just 1. But 100 cubed, think of the zeros it has as in terms of like what you want to be, I guess, multiplying. So you have 2 zeros here, and there's 3 that you want to, so you want to cube it. So you want to do these 2 zeros 3 times. So you have 0 0 0 0 0 0. This whole number right here is 1 meter cubed. It's going to be 1 million centimeter cubed. And to shorten this even more, you can just write 10 to the 6, because if you notice, if you move this decimal place in a different color, actually, 1 2 3 4 5 6, it's 1.0 times 10 to the 6, or just 10 to the 6 centimeters cubed. So it means that whatever you have in meters cubed, you can just multiply it by this factor to get to centimeters cubed. So that's what you do there. Let's see how we did in regards to the actual question. So exactly, they said that 1 meter is equal to 100 centimeters, which is good, and they converted it, which you have to cube everything, and they do exactly get 1 times 10 to the 6. Therefore, as they say, 1 meter is equal to 1 times 10 to the 6 centimeters cubed. So with that, this is correct. So just going to review it, just to make sure that you do keep track of your units. That's usually how you approach these questions. Now, with that, let's move on to question 2. How do you convert quarts to gallons? So I'm sure you've already seen the answer, but hopefully I was able to skip over for those that have not looked over yet. So you want quarts to gallons, right? So don't specify how many quarts. So actually, what we're going to do here, we're going to write X quarts. Okay? So it could be any number. Sorry, wrong type of quarts. And now we want to convert to gallons. Now, as you remember, because the quarts is a numerator here, you want it to be on the opposite side when you're multiplying. So you want it to be in the denominator here, and you want gallons to be here. And now you're probably wondering where you get these numbers from. You do have to refer to your conversion sheet. Sometimes, but rarely, your teacher might ask you to memorize them. But it's just important that you know exactly where you're putting your units, so that way you're multiplying correctly. So with that, let's see what they say for volume. We have 1 gallon is 4 quarts. So we'd actually write the 4 down here and the 1 up here. So that would mean when you cancel all these things out, you have now 1 over 4. So that's going to be x over 4 gallons. So this is going to be how it converts over. So let's say we had any number. Let's say we started with 5 quarts. Based on this, you would have 5 over 4 gallons or 1.25 gallons. Let's say we had 16 quarts. Same thing, 16 divided by 4, you'd end up with 4 gallons. So this right here is just showing you how you convert quarts to gallons. The important thing I'm just going to emphasize is that, as you can tell, make sure that your units cancel each other out. If you started out with a numerator, you want it to be in the denominator. A perfect example is like when you see questions that have miles per hour. To change hour, your hour would actually have to be in the numerator when you multiply it. Like you want to change hours to minutes, for example. This is usually the trickiest part of these questions. Although this one is a more simplistic form when we're doing the quarts to gallons, it's just important that you write your steps out fully in these forms so that we have an easier time keeping track of your units. Okay? Alright, so now let's move on to question. Actually, let's see how they did. 1 gallon is equal to 4 quarts. Yeah, exactly. So, yeah. They just stated straight from the table, which is perfectly fine too. But this is now, you've been given hopefully a tool you can use so that whenever you're actually given a set amount of quarts or gallons, you can convert between them. Okay? So, now then, question 3. Oh. Let's see here. We want to know, what is a molar mass of aluminum? Okay. Molar mass of aluminum. So, for this question, we have to refer to our periodic table. The reason being is that, sorry, give me a quick second, my nose is itching. The reason being is that when you're trying to solve for these questions, if you just don't really know what type of element aluminum is, then you have a hard time proceeding forward. Okay, so let's look at the periodic table here. As it shows, aluminum is right here, number 13, element number 13, aluminum. So now we know that there are certain types of elements that come in pairs, but luckily for us, aluminum is not one of them. It's just a type of metal. The reason why I say we're lucky is because that way we know that aluminum in its natural state just comes by itself. So it would actually just be written like that, solid. That's probably what you see in nature, just aluminum just by itself. You wouldn't see like Al2, that's not a thing or anything like that. So knowing that, because there's only one aluminum, to find the molar mass, we can actually just refer straight to the periodic table. So what does this say? The molar mass of aluminum, then, because there's only one, is just going to be straight from the periodic table. Is going to be 26.982 grams per mole. That is a molar mass of aluminum. The reason why it's important to know how it appears naturally is because you may be asked questions like, what's the molar mass of nitrogen, or better yet, like fluorine, for example. But these gases actually show up in nature usually like this or like that. So it's just important to know what their natural state is, because it's sometimes not just straight from the periodic table, because although this is a molar mass of, for example, 1 fluorine, in nature fluorine comes in 2. So when they say molar mass of fluorine, they're actually saying what is the molar mass of F2. Okay, and now let's see here. Yep, it's mass in grams of 1 mole of the element. So just determine it by just looking straight at it, which is what they did. And the molar mass of aluminum is indeed 26.982 grams per mole. So now let's move on to question 4 here. Ooh, wrong color. So what is orbital notation? For this, to understand this question, we do really just have to look at the periodic table. Let me just write it here. What is orbital notation? Okay. So I'm sure you heard of the different types of notation where it's like where you want it in its like SPDF form and stuff. But that's not orbital notation. Orbital notation specifically refers to the way the electrons are positioned. So with that, it kind of follows a similar structure of trying to find I'm trying to remember the name of that type of notation. I believe it's called the electron configuration. They're quite similar, but orbital notation allows you to see in terms of like the, I guess, directionality of each electron. So rather than continue to try to explain it, it's better with examples, and it's best to start really with the first element, hydrogen. So hydrogen actually, and not H plus, just hydrogen. If you wanted to draw orbital notation, you will still have, I like to personally to put this like the SPDF, and you fill it as you go. But hydrogen, exactly, just have 1 box, and you have to ask yourself, how many electrons does hydrogen have? Only 1. So that will be the orbital notation of hydrogen. Okay, now let's see if we can make it. Let's skip ahead. I'm not gonna go through each and every single element one by one, but let's go over the boron, for example. Now, as you remember with boron, right? I mean, if you wrote it in its other form, electron configuration, you could write, sorry, I don't know why that's showing up. There we go. So you could write, in a sense, for boron, right? You start with helium. Actually, I'm gonna write it right under. You start with helium, and then you know that it's S2P1. So 2S2 2P1. That would be boron. Now if you wanted to turn this into an electron configuration, same concept. You still want, because exactly, it becomes really tedious to write down everything, and the goal for the orbital notation is to note its valence electrons, so you don't have to go and list down everything. But instead of it being like 2s2, you still write 2s here. Oops, yeah, 2s. This would be 1s for hydrogen. Sorry about that. It's important to know, because that way you know what shell you're on. Okay, so boron, the reason why we put the 2 there is because, indicated by helium, its first row is already filled up. So 2s, and we want another one for 2p. Okay, and just like that, we do the same thing. It filled up this and just has 1. So that would be how you draw it for boron. Now, I hope you're starting to slowly understand how you do the orbital notations. I'm just going to check through just to make sure. Exactly, see? And now, let's say we had a really big but familiar element. Let's try bromine, or let me see, 1, 2, 3, Trying to think of an element that would be a good example, but also not too complicated. Let's try. I know there's an element that we could do. Let's try chromium. Okay, that's a pretty good choice. So, with that being said, chromium starts with argon. So let me just write it here. Okay, oops, chromium, right? So it starts with argon, that's what we have. And it's important to, usually I just put the electron configuration first because it helps me orient myself. So it still has 2s2, okay? Whoops, not 2, sorry, because now we're in the next row. 4s2, okay? And then we want to know in terms of this, and because we're dealing with the D row now, it'll be 3 because you have to subtract by 1. D 1 2 3 4. Okay, so the interesting thing is that this actually is incomplete because you actually want in terms of the rows, you'll notice actually when we write in orbital notation, you'll see why this answer changes, which is why the orbital notation is actually quite handy. So let's actually write this out. So we have AR, whoops, okay, and then we have 2 3 4 5 3D 3D 3D. And the reason why we have 5 here is because technically, like this one up here, we would have had 2 more because the P rows can fit up to 6 electrons and the D row can fit up to 10 electrons. And then the reason why when we have 1s is because it can only fit 2 electrons. So if we actually drew it out, as we said, 4s2 3d4, and the reason why I organize it, by the way, 3 instead of in front of the 4 is because you always want to make sure that when you are writing it down that the lower number in front comes first. So 4s2 and 3d1 2 3 4. So now you notice something, right? This 4s here is actually full, but this 3d is empty. For stability's sake, surprisingly enough, chromium would actually rather give out one of the one from the 4s and put in the 3d, so that way it becomes more balanced overall as an element. So it would actually be like this. So knowing this now, actually it would actually be AR 4s1 3, whoops, sorry, I was 3d5. You want to start with the lowest one first. 4s1. This right here would actually be the orientation for chromium because this is more stable, having the first, I guess, having each shell filled at least once first before moving on to the second shell. So that, and you will notice that if you count out, right, yes, technically it has 1 on its most outer shell, but these 3 here also can kind of participate. Whoops, I'm really bad at counting. These 5 here can actually also participate in, you know, the whole electron configuration. And, you know, in total you have 6, right? And funny enough, when you count in the periodic table from potassium, 1 2 3 4 5 6, that corresponds with its position on the periodic table. Okay, so that was just a much more loaded question, but the overall point is that when you're asking for orbital notation, this is what they're asking to provide. And you notice that if we didn't have, you know, the shortcut notation where we started with argon, it can get pretty extensive trying to list every single electron shell going up or down, hence why we do use those as well, similar to the electron configuration. So let's see how they did. Yeah, it is electron configuration. Nice. So You would think that the names would be switched around, because electron configuration looks to me more like this, and the orbital notation looks to me more like that. But hey, just make sure you know your terminology so you don't end up writing the wrong thing down. So let's see, positive spin, yep, and then the negative spin for the one pointing down, and yep. So for example, boron, they did exactly 2s 2p. Now you're probably noticing exactly boron, technically, right? You could move one here, but it serves no purpose, because the issue with boron is that it still has this row here to fill, so it wouldn't make sense for it to move an electron over here when it will still be unstable. So it kind of has like weird priorities here. You would even see something like, let's say in the periodic table it was, instead of boron, let me think, which one would have, maybe even carbon, for example. Carbon is one of those strange ones, because if you wrote it down, it would technically be 2s 2p2, okay, but if we wrote it out, technically it would be like that. Whoops, sorry, skipped right ahead, like that, right? So 2s 2p 2p 2p. Technically this electron here would be better stable, in my opinion, over here. So instead of it being 2s2 2p2, technically it would be 2s1 2p3, just because that way it would, I guess, be better stable. It honestly depends. This one I'm not too 100% sure about, but just going for exactly like you would notice that it is not as surface value as you think, as in there's a lot of things to consider of which position the element would prefer to be in. But yeah, so let's move on now to question 5. Okay. In fact, let's find out together if that's, because I am actually quite curious. Just a quick search, because if that is how carbon would like to orient itself, it does explain a lot more things. If not, then it's kind of, I guess, more so on the D and F rows if we get that far. So carbon, so carbon 2s1 2p. Oh wow. Let's see. Oh, I see. Okay. That makes sense. So this, the reason why it would actually be like that, so it would be 2s2 2p2, and this is why it's very important to know your electron orbitals and everything, just because even I can make mistakes too at this point. But the point being is that the S and P shells, which you'll learn later, there's not much energy difference between those shells, so there's no real priority. So I know I was discussing that earlier, that I wasn't sure about the priority, but you see the D shell, that one, exactly, like you notice right away that it's even already different from the S and P, as in on that row in the periodic table, all of a sudden, instead of it being the 4, it'll be referring to the 3D shells. So there is quite a bit of an energy level difference between the P and the D shells, but there isn't that significant of an energy difference between the S and the P. Hence why carbon is written like this. And not only carbon, but if you see any of the elements that are actually in this row here, I hope you can see the ones I'm highlighting. Those ones are the S&P culprits, I would say, and those ones exactly you don't have to really balance out or anything, because those two shells are quite similar in terms of energy. So now then, let's move on to question 5. My favorite question, actually: accuracy versus precision. So, what is accuracy and what is precision? The way I like to always explain these is simply like first by drawing, you know, those targets, right? So, I draw 2 of them because it's easy to distinguish there. So think of the left one as accuracy and the right one as precision, okay? So, let's say I was throwing a lot of darts, okay? And I would sometimes hit here, then I'd hit here, then I hit here, then I'd hit here again, then I hit here, then I hit here. Okay, I'm kind of all over the place, but then I hit here, okay? And then this other person that I knew was throwing darts, right? And you'll hit here, 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 here. Okay, this right here, which one of the two were more accurate, me or my friend? Now, the way you figure that out actually is because you notice that there is, you know, when you're playing darts, right, the most points typically, you know, is hitting the bullseye. I was more closer to the bullseye more times than he was, making me more accurate. Like, my aim may not be, you know, actually I don't want to use that word, but point being, because then I'll give it away, but my aim may be all over the place, but in moments I was more accurate than my friend, meaning that overall, you know, spatially agreeing, because that's why I put it kind of in this corner, that I was just more accurate than him. Now, just as on the flip side though, he would be more precise than me. Why? Because although for some reason he can't hit that bullseye, he can always end up hitting close to where that spot was, so making him more precise than me, because I'm all over the place. You see the distance here, and there. Like, there is really no precision exactly to my throwing the darts, but his is all focused around this area, making him more precise. So the way this applies to chemistry is because when you're running experiments, right, sometimes you are given like a literature value, something that's actually like the actual value you want. Let's say you're doing an experiment to find the boiling point of water, and you know that it's supposed to be 100 degrees Celsius. Oops, yeah, that's a boiling point. Yep. Being accurate, for example, would have readings as close to 100% as possible. 100 degrees Celsius as possible. But some of your classmates might have like, you know, 90%. 95 degrees. Some might have 102 degrees. Some might have, you know. But the more you have at the actual 100%, I keep saying percent, 100 degrees, that emphasizes the more accuracy you have. You know, and that's usually calculated like, you know, it's usually an average of you know, of data minus actual, well, what did I say earlier? The textbook literature, exactly, literature value. Okay, and you want the absolute value of it because you don't really care about directionality, times 100 to get a percentage. Oops, I definitely missed a step there. Divided by the literature value, because it tells you the magnitude of how far you're off. Okay, and then all this times 100. Okay, this is usually the equation you use to calculate accuracy. Now let's say exactly in the example I gave with the whole what's it called, boiling point in water. So let's say your average in the class was 102. Okay, so that's 102 minus 100 over 100, and you see that, you know, times 100. But in a sense, you get 2%. Okay, and that means you would have 2% error. Okay, that would be calculating your accuracy. So you can kind of tell based on the whole example with the dartboard, that the more you have close to the actual empirical, there's a word, empirical value, like the literature value, the more accurate you can be. Because you notice, right, if we actually use my friend zone over here, right, although his were in the spot constantly, they were all each around the same away from the literature value. So this one, for example, like you know, you could have in the accuracy one, like in my own here, right, it'd be like 98 degrees plus 100 degrees plus 102 divided by 2. But this one would be like 104 degrees constantly divided by 2. So then this one would have, when you do the math, it'd be like 4% error. So it's like this one was less accurate. Now, precision, that one is a little bit more complicated to calculate because you need a little bit of statistics, but it's actually found by the standard deviation. So unfortunately, I do not remember the standard deviation formula off the top of my head, but the goal is, in a sense, to see how much your data varies within itself. So considering, let's use my my dartboard real quick. It'd be like, let's say we had a value exactly, an average, as you said, it was 102, right? Okay, but you notice that the bars, right, would be kind of big because, as you noticed, they were kind of all over the place. So that would be an indication of not that much precision. Now this one would be at 104, but its deviation will be like that, making this one more precise. Now I promise, you know, one day when I do remember that standard deviation formula, I will let you know right away. But it's something about, you know, calculating like it's like the difference from the means, and you keep doing that, and they divide by the amount of tests minus 1, something like that. It's, I believe it's something like E, sum of the mean minus X over N minus 1 or N, something like that. That's something like that, but I don't want to give you a wrong formula. Point being is that when you do use the formula for standard deviation based on the data you assign, you notice that the board I drew here, this one, would be more precise than this one here because the standard deviation would be smaller. Okay, and for the more accurate one, percent error is smaller. The reason why I love this question is because it actually fascinated me the first time I learned this in terms of the difference between accuracy and precision. So just loved explaining it every time. So with that being said though, let's see here in terms of how they explained it. Accuracy and precision. Precision describes how close your results are to each other. Yep, I'm glad I got that right. And the deviation of results is low. Wow, awesome. I'm really happy I was able to get that right. And that accuracy is defined as how close you are to the theoretical value, the literature value. And exactly the difference between the two is that precision doesn't mean that your results are accurate, and accurate doesn't mean that your results are precise. Exactly. So as you see this one, right, this person right here, the 2 that kept getting the 2 grams, that's pretty precise. That's pretty concise with each other. And the same with this one, I would say it's a little bit less concise. As you can see, the 4.95 and 5.03, there is more variation there, right? But that person is more accurate because he actually is getting closer to the experimental value. Yeah. Exactly. So that's what they said. They are precise, but it's not even close to the theoretical value. So now, with that being said, as the person mentioned here, right, precision doesn't always mean that you're accurate, but the important thing, especially in science, is that you want your results to be as precise and accurate as possible. It's, for example, like with the boiling point of water, right? If your experiment is set up to where someone can get 80 degrees Celsius as a boiling point, another person can get 120 degrees Celsius. Sure, on the mean, you're accurate, but that's not a very precise experiment, so you should be looking for ways to make it more precise. This can be applied in terms of medicine and everything, because just like the efficacy rate and everything, is that it helps when you're able to recreate your experiment, and experiments that aren't so precise are just hard to recreate, because every time you just keep getting a varied number, and it's hard to establish actual significance and correlations. So that's why precise, in my opinion, is quite important. But yes, exactly, like when you do have a value you actually want to reach, that's when accuracy comes into play. As in, if you can't reach that value, you also need to redesign your experiment. So these two go hand in hand, and I don't personally think one is more important than the other. These are just two things that you should really be thinking about whenever you run an experiment, as in, are the results accurate, and are the results precise? Lacking one of them just makes the experiment, I guess, personally to me, just less valuable, or just you should be looking for ways to change it. So, with that being said, this is still correct. So let's move on to the next question. Number 6. What are specifically ionic compounds? So, let's look at the periodic table. So, ionic compounds, to put it as simply as possible, it could have a lot of other things, but the goal is for an ionic compound to be a metal. Metal and non-metal. Okay? That is the basis of ionic compound. Now you're probably wondering, what are metals and non-metals? So you want to refer to your periodic table to that, okay? So as you can see here, this row, except for hydrogen, this row here, row 1 or column 1, just know the ones I'm highlighting here. These are known as it says here, the alkali metals, okay? You go over to column 2, alkaline earth metals. You go over to row 3 through 12, these are transition metals. And then you go over to kind of these ones over here, but I don't really personally trust these, and these too. But these count as, I guess, almost you could say pseudo metals. But the most things you should be focusing on are, personally to me, up from row 1 to 12. Actually, I write that down. Row 1, better handwriting. Column, 1 to 12, okay? And I won't put a star here because not including hydrogen. Okay, so that's what you want there, because the simple goal there, just to make sure. Okay, exactly. So the reason why you don't want to include hydrogen is because that's non-metal. Okay, you can actually see here when you highlight over this. And with that being said, typically the non-metals start at, I would say, row 14. Well, column 14 to 17. Not much really bonds with the noble gases, because noble gases, you're kind of exactly, they're noble. They see themselves as higher than everyone else, so they don't want to mix with anybody. Like helium, neon, they're just stable by themselves. They're the elements that are content with how they are. But everyone else, these are the ones that usually try to combine with each other. So that's typically how it is, but I'm gonna put an asterisk here because you want to pay attention to which element. Okay, so now that is a basis for ionic compounds. It can definitely get a lot more complicated than that depending on the question you have. Like for example, if I said CH3COO, right? H, this whole thing is not an ionic compound because you notice it only has carbon, hydrogen, and oxygen. But if I said it was CH3COO and A, this is now an ionic compound. Okay, because when they say metal and non-metal, they really just mean it has a metal part and a non-metal part. That's the key thing, is that in your giant, no matter how big your molecule is, although there may be limits, the point being is that if you have a metal part of that compound, it's an ionic compound. So just be wary of that. Always look out for it. Look out for things that aren't part of the non-metals, or more, if it's easier for you, just look out for things that are metals. Like this one is a common example because this one's actually sodium acetate, if I remember correctly, because it has a sodium and that's acetic acid right there. But yeah, so that's just an example here because this is still considered an ionic compound. So let's go back to that and see how we were to answer this, if we have anything else to add. So combination of two or more atoms, exactly, and that's a key word because they're compounds. You cannot be a compound by yourself. That's unfortunately how it works. So let's see here. Ionic compound, metal and non-metal, yep. And they're now explaining how it actually works. For these ionic compounds, typically what happens is that the metal, in typical sense, usually gives the electron over to the non-metal. So if you wrote it, if we chose exactly NaCl to make it a little bit more simple, when you wrote down the Lewis dot diagram, it looked more like this. In fact, let me just make one of these red because that will symbolize the one that sodium used to have. The point being exactly is kind of like that. You notice that the Cl and the Na are quite different now, as now the Cl is a minus and the Na is a plus because it lost it and the Cl gained it. So this will be that Lewis dot diagram for NaCl, and it actually corresponds as well with the formations as well, and it also explains why they dissociate so easily, because the sodium is pretty much said, here, have my electron, I'm going away. And that's usually what happens when you add salt to water. It dissociates and breaks apart. So yeah, exactly, the cation loses the electron, typically the metal, and the anion gains it, which is typically the non-metal. And exactly, and this is just so that they can be stable. This is how they prefer to be. And yeah, that is a whole thing for ionic compounds. Okay, so this is correct. Let's move on to question 7, but before that, do a quick water break again. A little thirsty. Okay, so now this is definitely a question. So with that, as it's saying how many grams of sodium acetate NaC2H3O2 has to be added to 1 liter of acetic acid. Oh, nice. So that was sodium acetate. Awesome. Because you can also rewrite that one as CH3COO and A. Yeah, because it has 2 C's, 2 O's, and 3 H's. So nice. That was sodium acetate. So with that, how many grams of that would have to be added to 1 liter of 1.5 acetic acid to make a buffer with a pH of 5? So buffer solutions, what's important about them? You want to have the acid and its corresponding conjugate base. So with that being said, let's see here, we have Na2, so we have H, oops, don't know how that changed. Oh, I'm in pencil. We have HC3COO, sorry, CH3COOH plus H2O turns into CH3COO minus plus H3O plus. So the reason why we write it like this, and you're probably wondering, where is the sodium acetate? So the thing is that there's a side formula here, okay? Sodium just completely dissociates to form sodium and CH3COO minus, okay? Like we discussed earlier in terms of what ionic compounds like to do in water, this is what would happen. The sodium completely dissociates and has no relation, which is how we get back to CH3COO minus. With that being said though, the important thing here is that you want to always have, to make a buffer, you want your HA, your acid, and your A minus conjugate base, okay? And as that formula that says there, you, to make sure that you have to find out the pH you want for the buffer solution, the formula you use is pH. So the pH you want is equal to pKa, which is the dissociation constant for that acid in question. In this case, it would be acetic acid, okay, plus log of A over HA. Okay, that is how you'd write it. This is right here is a formula you'd use to calculate it. Now, with that being said though, you notice in the formula there are certain pieces that you need. Okay, you need the pH, which is given to you. So we have 5.00, that's our goal, okay? pKa, this one needs to be known. So you can't just solve this question without knowing the pKa. Sometimes the question gives it to you. Sometimes you're given a data sheet that has pKa's. I doubt I have that data sheet. In fact, that would be something I'm going to add right now, because depending on the questions as we go on, we would definitely need to have pKa of common weak, pKa of acid and bases. Just a document that we're gonna start having out. Hopefully this one here will just have the pKa table. Oh, that's unfortunate. Might have to go to, yep, tables of acids. There we go. So this is what we're going to be using going forward. Hopefully we can still read it. And exactly, they did a nice job of saying which is stronger acids. And yeah. So with that being said, we want what's it called? Acetic acid. So as soon as I see it, I will let you know. 'Cause this is, there we go. Acetic. Sorry, I highlighted two of them. It says 1.76 times 10 to the 5 is the Ka. Okay, so they usually give you the Ka, and that's what we're going to use to solve, because 76 times 10 to the negative 5. Okay, because the other formula to find pKa is kind of like how you'd find the pH when, you know, not like this, but when you're just doing the pH straight from the how much hydroniums you have, it'd be negative log of Ka. Okay, so yeah, that would be how you solve that. So actually using that, we can actually find out what the pKa is and see if it matches at 4.75. So negative log of 1.76 times 10 to the negative 5. We do indeed get 4.75. Well, we get 4.76, but when we round, but yeah, exactly, it's pretty close. pKa is equal to 4.76, around there. So point being is that now we have these numbers, right? And we're trying to actually figure out now how many grams of sodium acetate. So we want to know how much of A minus we need to be able to make a buffer with pH of 5. So we need to reorganize this formula, but before we do, let's see in terms of how they tell us how many specifically how many, what's the concentration of HA, because this is all in concentration. And then once we figure that out, then we switch it over to grams. But let's see, HA, it says that 1 liter, so, and 1.5 moles of acetic acid. So we can ignore the 1 liter part, because the important things that they give us the concentration is 0.15. Okay, the 1 liter thing doesn't really apply here because we don't need the moles. Technically you could use the moles to solve it as well, but we're just looking for concentration because you can also get grams from there. Okay, so 1.5 m. Okay, so now that we've done all this, let's reorganize this whole equation. So it will be log A minus over HA is equal to pH minus pKa. Okay, and now we want to get rid of the log, so we want to exponent everything. So that'd be A over HA is equal to 10 to the power of pH minus pKa. Okay, and so that means A minus is equal to 10 pH minus pKa divided by, oops, not divided by, multiplied times HA. So 10 pH minus pKa times HA, and that whole step should give you the concentration specifically of sodium acetate. And then that's when, you know, based on the concentration, because it's based on the 1 liter, that's when we'd actually use it. But first, let's actually get the concentration. So we have now pH minus pKa. So we want 5, right? So 5 minus that 4.76, okay? And then 10 to the power of that answer. So 10 to the power of that, okay? We get 1.75, like on the dot. And then we want to now multiply that by the HA. This, it said it was 0.15. So we have now the concentration of A minus, okay, is 0.2625, okay? That is the concentration we get after reorganizing and you know, making sure that we have our units. So we have 2.2625 moles per liter, okay? But they're asking not for moles per liter, but for grams of sodium acetate. So first we got to find out how many moles is that. Well, luckily for us, we only had 1 liter. So if you multiply that by 1 liter to just get to moles, you would just have the moles is just 0.2625 N. Okay, that is a moles of NaCH3COO. Okay, now to get the grams, you need the molar mass, your best friend. So let's go back to the periodic table. You want to now add 3 hydrogens, 2 carbons, 2 oxygens, and 1 sodium. Okay, so sodium is 22.990 plus 3 times 1.008 plus 2 carbons, 2 times 12.011 plus 2 oxygens, so 2 times 15.999. Okay, and the molar mass is 82.034. If you want to break down the molar mass, just make sure exactly you're counting exactly how many of each element you have. That's the best way, and I'll just break it down here quickly for you. It's 1 Na, 2 C, 3 H, 2 O. That's just how you keep track of it to make it easy for yourself. So that's molar mass here, and we have 0.2625 moles, right? So as we know, in order to get to grams, we need grams in the top. That's what we want, and we need moles at the bottom. So 1 mole is 82.034 grams, and these cancel out, and so we multiply those together. You need 21.53 grams of sodium acetate to make a buffer solution of 5 pH. Now, with all that being said, let's see if we did this correctly. Okay? Exactly. So they did what we did. Okay? And then, so they have exactly, they had pK value of 4.78, and they retrieved it from the PubChem. So it just depends on where you get your values from, because although I'm pretty close, mine was a little bit different because mine was 4.76, so I had 0.24. So yep, but everything I'm seeing here, everything looks correct, and then they should multiply now with each other. Okay, 0.249, I did have 0.2625, so they do have the moles correctly of, the moles per liter, and then they can convert that to moles. Then they found the molar mass. This is good, and they got 20.42. So this is absolutely correct, and especially because as we were going through, you notice that because they had a smaller value, well, actually a larger value for their pKa, they ended up having a smaller value for the mass needed, because all the math checks out. I had a smaller value for pKa, meaning that my difference was larger, which is why I ended up getting a larger amount of grams needed. But yeah, this is correct. And what a question for question 7. Now we can move on to question 8. Okay. So, this is a good breather from what we just solved. So it's asking, what is 29 degrees Celsius 2 degrees Fahrenheit? So in this one, we can't really solve it the same way to just going from unit to unit, because it's not a direct conversion. There's also an element you have to add and subtract. So they're trying to get to Fahrenheit, right? So you want to make sure, right, that your Fahrenheit is what you're solving for. Okay, is equal to x degrees Celsius times 9/5. I'm just taking this straight from the temperature conversion sheet here. Depending on the course you're taking, if you're using this the equation constantly, your professor might ask you to just memorize it. So I would definitely keep track of, all this stuff. So with that being said though, let's see here. We just plug in our X value, and let's see, 29 degrees Celsius times 9 over 5 plus 32. So just plug into our calculator here, 29 times 9 over 5. So because I'm Canadian, 29 degrees is a fairly warm day, almost bordering hot day. So we should be expecting something like that in terms of Fahrenheit. Something that's like close to like the 100, something like that. Because those are usually like the ones that start to get uncomfortable. So 29 times 9 over 5 plus 32. Okay. 84.2 degrees Fahrenheit. So that is well, I used to live in Texas, so I'm surprised it's actually that low. I guess I was just used to more hotter days. But degrees Fahrenheit, 84.2 degrees. Hopefully we got all those steps correct. And yep, that's exactly what they were able to get as well. So that is how you would go through in terms of finding the Celsius to Fahrenheit. It's important that you note that you can either have to memorize this equation or just refer to like the conversion sheet that you may have been graciously given. But yeah, that was a nice little breather from that previous question. Okay, now let's move on to question 9. What is the empirical formula for magnesium oxide? So let's refer over to the periodic table. So magnesium is on the second column, okay? And oxygen is on the 16th column, right? What does that mean in terms of valence electrons? So magnesium has 2 valence. In fact, actually, this is a good practice to actually do our electron configuration. So magnesium, right? Because in the third row, it'd be neon, and it'd be 2s2. Okay, that is it for magnesium. Oops, I keep putting it in the wrong place. It wouldn't make sense. It's 3s2 because it's on the third row. Okay, and oxygen is now helium. Okay, 2s2, 2p4. Okay, so this tells us how many valence electrons we have. So magnesium has 2, oxygen has 6. Now, as you know, elements like to be whole. It is like 8, and sometimes they either want to gain more or lose some. Magnesium conveniently can actually give away 2 of them, and oxygen can receive 2 of them. So it's a 1-to-1 ratio here actually. So it would just be, for the empirical formula, it'd be MgO, because the fact that it only takes 1 magnesium to give away 2 electrons, and only takes 1 oxygen to receive 2 electrons. So it'll go over there, and it'd be, in a sense, Ne just plus, and oxygen would be able to be Ne as well, because it'll be able to be filled up there, 2 minus, theoretically speaking. But yeah, in terms of what's happened, it lost that, and this was able to gain to get to 6. But yeah, that would be the empirical formula for it. This is just to make more sense of the electron configuration. Usually you can figure it out by looking at the position on the periodic table, and you balance from there. But for magnesium oxide, this is what you get. Exactly. So magnesium, as they show, it gave away its 2 valence electrons, and oxygen has 6 valence electrons, so it wants to gain those 2. So that's the formula for it right there. And you can simplify it to get rid of the 2's on each corner, and you end up with MgO. Okay, and now let's go to question 10. How do you find the molar mass of argon? So give me a quick second. Just gotta refill with water. So, how do you find the molar mass of argon? Let's go refer to our periodic table. Okay, we see argon as element. Actually, let me actually write down molar mass of argon. Okay, and we have that is element 18. So we first need to find the molar mass, you need to locate element. Okay, and we see it here. It's a noble gas. Okay, now I know that gases like to be in pairs, but noble gas specifically, those, you know, they don't really need anything else. Their valence shell is completely filled. They can exist in nature completely by themselves. Okay, so that answers that question in terms of like whether it be alone or together. It would just be like that. This would just be argon. Okay, and now with that being said, to find the molar mass, you'd refer directly to the periodic table, and you see the number under the name right there. Okay, that actually is a molar mass, so 39.948. okay, this would be the molar mass, grams per mole, because it doesn't come in pairs or anything. It's just argon by itself. So exactly, that's all you need there for it. So this would be the molar mass of argon. Let's see. So it's talking about the periodic table and the information it gives you. So exactly, and they're referring now to the atomic weight. So the interesting part here is that because they actually have the atomic weight, it would actually equal to the molar mass as well for elements that can appear as themselves. So exactly 39.948. All right, and now that we finished question 10, let's move on to question 11 here. What is the molar mass of sulfuric acid? So let's think about this question real quick. This is how we did for the previous question. We were finding the concentration, or the grams of the conjugate base. We need to, let me see, what is molar mass of H2SO4? So that is sulfuric acid. Okay, so just as how we did before, we want to write down every constituent. So we have 2 of H, okay, and 2 of, 1 S and 4 oxygen. Okay, and then so we now add these together, we'll multiply. So now let's see, hydrogen 1.008, that's 2.016. Sulfur is 32.06, and 4 times 15, sorry, I cannot do that in my head, 15.999 times 4, 63.996, and we add these all together, so plus 32.06 plus 2.016. So for those that are wondering where I got these numbers from, I'm using the molar mass of the individual elements, so the atomic mass, okay, and I'm multiplying it by how many of them are there. So hydrogen was 1.008, as you can see right there. So this is how we're getting these numbers if you're curious. Okay, so now when we add them together, we get a molar mass of 98.072. okay, so sorry, give me a second. And now with that being said, this is really all we need for the molar mass, because now we have the grams per mole of all the constituents together. So this right here is a molar mass of sulfuric acid. Let's see if we did that correct. So, yep, hydrogen, sulfur, oxygen, and you multiply them by constituents, 2, 1, 4, and 98.09. They got a slightly different number because, as you notice, their hydrogen was 1.01, and their sulfur was 32.07, and their oxygen was 16.00. Okay, so this is correct for question 11. Okay, and now let's move on to question 12. Is SF4 polar or non-polar? Now this question, this is a little bit of a doozy. So SF4 polar or non-polar? So first of all, how does SF4 even organize itself? That's actually the tricky part. So sulfur, okay, as you see on the periodic table here, it actually has 6 electrons. Okay. Oops. So it would look kind of like this. Okay, that's sulfur. Okay, and fluorine has 7 electrons. So here we're actually going to try to draw a Lewis dot diagram because that's the best way to observe the molecule. So sulfur exactly is 6 valence electrons, and fluoride or fluorine is 7 valence. Okay, now this is the part that unfortunately just comes down to memory, because there's some elements out there that don't really care as much about the rule of 8, as in, you know, wanting to have 8 electrons, because sulfur just kind of blows out the water and says, you know what, I honestly don't really care, so let me just accommodate for everybody around me. So I guess you could say sulfur is nice in that sense. So interesting enough, this will be that, and I'm going to write the fluorine in green, okay, because it'll bond here, and this is easily to keep track of the 7. So, okay. Okay. So that is SF4. For some reason, sulfur says, I'm okay with having 10 valence electrons. And the fluorine gets everything they want. Each fluorine is like, yep, 8 each. So if you see here, so if I circle in blue, 8, 8, 8, 8. Okay? And you notice exactly that if you add it all together, 6 plus 7 times 4, 34, right? And 8 times 4 is 32, plus these two here, 34. So they do match. So now they're asking if it's polar or non-polar. So for this, now that we know the, drawing the Lewis dot diagram, we can kind of draw the molecular structure, allowing us to see if it's polar or non-polar. So the molecular structure for SF4 will kind of look like this. No, I think I got that one wrong. Oh, okay, yeah. Yeah. Or is it like this? Something like that. There we go. So, let me actually review this based on my information here, because I would love to make sure that I actually do this correctly. So, with that, sulfur kind of looks like that, well, SF4, where there's an electron, and then the rest of them kind of stick out like that. Let's see here. Nice. So that's kind of what it looks like. In fact, these are slightly bent because that's how strong the lone pair is. But yes, this would be how SF4 looks. So now right away, actually, because we drew the Lewis dot diagram, you can actually should be able to already tell whether it's polar or non-polar. But this molecular structure should actually hint at it a lot better. But the point is that once you have a valence electron there that is not counteracted by another valence electron like on its opposite side, which isn't really possible with this arrangement here, it's polar. The lone pairs just have the most pull in terms of electronegativity. So you notice that they kind of like, even though fluorides are pretty strong, kind of pull like this. It'd be polar towards that valence electron. I mean, not valence, the lone pair, because a lone pair is just as electronegativity as you get, like they're actual electrons in body form. So the answer is that this would be polar because there's no balancing out of this. There's always going to be a directionality towards a lone pair. So let's see here. They decided 3D structure, and it has a lone pair, and because it has a lone pair, it's polar. So that's why Lewis dot diagram is important. But if you can't figure out from the Lewis dot diagram, then I definitely say draw out the also molecular structure if you can. These are some of the things you kind of have to memorize. Even I'm getting familiar with them, hence why I have to refer back to my book. But the point being is that once you get familiar with that, you start having a much easier time telling whether they're polar or not. Okay, so let's move on to question 13. Okay. So, with that being said, what is the Lewis structure for chloro? It's not as fun when the answer just was right there, but let's just try to pretend like it's not there. What is the structure for, I'm going to write that whole name down, CHClF2, okay? But actually the name gives a big hint, okay? Because the point being is that usually, what is the structure? The way we answer this question is, what's the structure for methane? Methane is CH4. What does that look like? C. Oh, and it asks for Lewis structure. So C. H. 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 That is a structure for methane. Reason why I drew it like that is because for methane, carbon has 4 valence electrons, hydrogen have 1 each, so in total should be 8, which is what we get here. Okay, now CHClF2, right, which is chlorodifluoromethane. Imagine having methane, but now you replace 3 of hopefully this is copy and paste. Nice, it worked. Exactly, it's the same exact thing, but now actually you replace 3 of the hydrogens with the corresponding elements they mentioned. So this gone, that's gone, and now we have ClFF. In terms of the order of how you put them, it doesn't really matter because at the end of the day, the chirality still balances out, just as long as you have the right elements there. But this right here would just be the Lewis structure for it. Okay, and if you wanted to double check, chlorine has 7, fluorine has 7 as well for valence electrons, so that's 21 in total because fluorine there's 2 of them. Carbon has 4, hydrogen has 1, so 5 plus 21, you should have 26 in total. And what do we have here? I'll use a different color actually. We have 8, 8, 8, so that's 24, and 2 more, 26. So with that, hopefully that was a good example of how you draw your Lewis structure for this molecule. So let's see here. They do use bonds instead of actual electrons, and depending on your professor, that may be correct or not. I'm just gonna say this is correct because they do understand the basic concept of it, but I would always err on the side of using the electrons instead of just a bond, because when they ask for Lewis dot diagrams, from what I remember, they just want everything to be in electron dots. So now, let me take another water break. And now let's move on to question 14. Okay. So, let's see here. How many valence electrons are in carbon? How many valence electrons in carbon? So with that, we refer back to our periodic table here, and in fact, I could just say that, oh, if it's on the 14th column, that means it has 4. But let's actually break down what that means, okay? And we actually did discuss this earlier in the day. So as you remember, carbon, right? Okay, when they run it electron configuration, okay, it starts with helium, and now we go straight to the valence shell, 2s2. Okay, based on the 2 over there, lithium and beryllium, and then 2p2. Okay, you add those 2 here in this corner together. That's how you can tell how many valence electrons carbon has. That's 4, because they're both in the second shell. Okay, and as we discussed earlier, the s and p shells don't have much of an energy level difference, which is why they can be counted together. Hence why carbon has 4 valence electrons. Now let's rewrite this in orbital notation even, because you even see there, okay, 2s, 2p, 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 okay? And let's see here, we have 2s2, so it's completely filled, 2p2. Still the same thing. The energy level across the S and P's don't vary too much, which is why these 4 red lines, whether they're pointing up or down, indicate the valence electrons of carbon. So with that being said, we can say for definite that carbon has 4 valence electrons. Now I did it this way just so that way we can use the concept we're learning throughout, just to be able to provide a form of association. But you can also just really just look at your periodic table, and you would notice that if you start from the first column, right, including hydrogen actually, the first column indicates 1 valence electron, second column indicates 2 valence electrons. Now instead of 3, you would actually skip over all the row of transition metals. So all this right here, you actually skip over and go to 13. Luckily for us, it is 13, right? So think of it as just subtracting the 10. 13 has 3 valence electrons. 14 has 4 valence electrons. 15 has 5 valence electrons. 16 has 6 valence electrons. 17 has 7 valence electrons. And 18 has 8 valence electrons. So considering that carbon is on the 14th column, it would also have 4 valence electrons. Okay. So let's see, they gave so they went straight for the whole group number as well, which is also a good way to do it as well. When you get to a little more complicated and start dealing with transition metals, that stuff can get a little bit hectic and determine the valence electrons. So it's just good to always draw out the whether it's electron configuration or the notation that we did here as well, the orbital notation. So this is correct, and hopefully exactly when they ask how many valence electrons they have, they're referring to the elements on like either side of the periodic table, not the ones in the middle. Okay, so now let's move on to question 15. Ooh, how to determine molecular shapes. We did actually touch upon that when we were doing the question about sulfur tetrafluoride. So to determine molecular shapes, determine molecular shapes. Okay, so like I was saying, exactly, we did kind of touch upon this when we were doing the backing out the sulfur tetrachloride, right? But the goal here, right, is that whatever formula given, I'm actually just going to read off the answer because I do actually agree with it. You want to identify the bond pairs. So let's say exactly, let's use actually the example of sulfur tetrafluoride, right? We did the Lewis dot structure, right? Where sulfur kind of just like, yeah, whatever, I don't really care about having 8 shells. Okay, we were able to squeeze in all fluorine. Okay, and based on the Lewis dot diagram, I could probably draw these farther apart. Based on the Lewis dot diagram, we're able to actually identify the bonds, which it goes like this. This is a bond, this is a bond, this is a bond, this is a bond. Okay, and it says you need to identify the bonds and the lone pairs. So we're going to circle the lone pair in red. So it has 4 bonds, 1 lone pair. Okay, so this shape would be, if I remember correctly, it's kind of like there's no word for it. It's like a K. It's like a K shape. Let me see here. Do they have it? Nice. Oh, did they go far enough? 6. It's like 6 electron groups. Oop, sorry, I lost my. There we go. So exactly. So, and these are actually counted, right, as electron groups, whether it's a bond or a valence electron. Now, the reason why I say that is because how many electron groups does this have? You would say 5 electron groups. Okay, and now we can refer back to our handy table that this person was able to leave here. And how many lone pairs does it have? Trigonal bipyramidal. Okay, that's the term for here because it has 5, but it has 1 lone pair, meaning that it will be a seesaw. And they actually provide an example here: tellurium tetrachloride, also sulfur tetrafluoride can do the same thing. And as they mentioned, in terms of the seesaw, it would look something like this. I did draw mine a little bit different earlier, but this is kind of like what they mean, the by seesaw at least. And so, with that being said, here are the 4 fluorides. Okay, and you notice that this is kind of like, although I drew it to the side, think of it as a circle that goes like this. Okay, and the fluorine is something that goes through it, the midpoint there. Okay, whoops, that's not a good there. Okay, so we have 1 fluoride there, 1 fluoride there. Okay, the 2 fluorides there. Okay, because remember, this is a 3D shape, and up here you would have your lone pair. Okay, and the reason why I drew it like this, because when lone pairs exist, right, you see this angle here, typically it would be 90 degrees, typically, but because the lone pair pushes literally everything away from it, you would know that this angle here and this angle here, well, I'm only going to draw one of them. I'm going to leave that in blue as well, right? It'd be less than 90 degrees. Just something, that's all we know. From that to a center point. In fact, I'll draw it at a different angle. Because now we know what if this was the circle, right? Okay. Exactly, so this angle here is going to be less than 90 degrees. Okay. Okay, and now when we refer to the actual circle, right? The distance between these two, I'm going to use a different color now. These two here, right? Typically, if we had it completely full, right? You'd actually have a wheel, okay? Like that. And each one, okay, would be around 100. Let me just make sure I'm doing the math right. 120, okay? Because 120 times 3, that's 360. But because we have now, instead of like just a normal bond, right, it's going to be that like lone pair. To push a little bit, so this bond actually is just less than 120 degrees. So that's just breaking down what this shape is, specifically because we did talk about sulfur tetrafluoride. But that's in a sense what I'm trying to explain, how it looks like that, okay, and how it's like a seesaw. You see, you have two ends and like two legs down there, and that's how you form the seesaw. I drew mine kind of facing, like, if I highlight this, and I can actually, can I turn this thing? No, I cannot. So, but I drew mine kind of facing this way with the lone pair like that, but it's still the same effect, okay? Because exactly like as the molecule floats around the ether or whatever, it can orient itself differently. But exactly, that was just one example. But the key thing being is that you want to be able to identify your electron groups, whether they're lone pairs or actual bonds, okay? And the reason why I say bonds is because you have to remember that even double bonds still count as one bond. So I'm trying to think of an example here. If I had like that, like CH2O or something like that, right? This would still actually be 3 for the electron groups, okay? And it would actually just be trigonal planar, like flat down, just like how we kind of drew that circle. It'd be just like that. And H. That's actually what it would look like. Although it would be polar, because oxygen would be doing the most. Because it's polar and hydrogens don't really do anything. That's what it would look like there. So point being is like double bond, triple bond, single bond, these all count as one electron group, okay? And then you need to count all of them together. So that's how you even get the linear ones. For example, if I had CO2, it'd be an electron group of 2. And you know this is a linear straight line, okay? So these are just examples I can think off the top of my head. But yeah, hopefully that explains the shape. And this is as far as it goes. So 6 electron pairs, P F6 minus. So there's an extra one. So if we have phosphorus, for some reason it doesn't also care about it will look kind of like that, phosphorus PF6, okay? And it kind of forms a perfect box, hence why it's called octahedral. It would be like 2 planes intersecting. I wish I was better at drawing 3D shapes. So it'd be like one plane here and one plane there. Nope, that's not a good look. It pretty much looks like this, okay, when you look at it from the top view, and also looks like that from the side view. So every angle here is a 90-degree angle. And that's only if they're like actual elements, because everything changes once you throw in a lone pair. But yeah, so that's just kind of drew shapes all over the place. But that's how you determine molecular shapes. The key is, as I'll say again, the electron groups. So Lewis dot diagrams are your best friend to figure that out first, and then from there you would draw the molecular shape. And it kind of does take some memorization, because especially when you start dealing with bigger molecules, the molecular shape is not as apparent when you start involving low pairs as well. So there is conveniently a list, as you know, the person even wrote down here, but with the actual picture as well is just quite helpful, so you can actually orient yourself to which shape you want. So let's move on to question 16. Okay. How do you find the molar mass of iron oxide? Okay. And the cool thing here is that this is a side note, is because iron has certain oxidation values, but this is iron 3 oxide. How do you know it's iron 3? Because you need 3 oxygens to balance this out. So it'll probably be like Fe3 plus and O2 minus. So for it to have the same amount of like to have a neutral 0, you need 2 of these, so 2 Fe3 plus, and you need 3 of these, 3O2 minus, to get 6 on each side. But yeah, let's find the molar mass. Same concept here that we've been doing. Write down the constituents and how many we have of each. 2Fe3O. We refer to our handy periodic table, and now we find the atomic mass, or just the molar mass of 1 iron, so 55.845, and oxygen was 15.999. So 2 times that and 3 times the other one. 845 times 2 and 15.999 times 3. And now let's add. So that is, oops, skipped right over it. 1.69 and 47.997. Okay, so now let's add it together. What do we get? We get 159.687 grams per mole. And this number right here, this will be our molar mass for iron 3 oxide. So exactly, that's what we did. 2 of 55.845 times 3. 2 of that, 111.69. 3 of 16, yep, 48. 159.69. So this is correct. And as they're actually doing there, for all these questions we've had, it's important, very important, to always put down your units, and it is grams per mole. So let's move on to question 17 here. Is ammonia, NH3, an acid or a base? So for this one, actually, it actually helps for me in terms of these questions to actually write down the Lewis dot diagram, because it allows you to see if it has space to even accept or give away a hydrogen. Ammonia is a special case because it's one of those things where it doesn't follow your typical rules. You see it has so many hydrogens, and you're probably wondering, why does it just give one away? So let's draw a Lewis dot diagram. It has a nitrogen in the middle. Remember, it has 5. Okay. And actually, I'm going to do a much more prominent color. So this would be NH3. And this is already neutral, right? Okay. So this has a hard time giving away its hydrogens, because these aren't just any bond where you're like, oh, hydrogen give an electron, right? It loves these hydrogens so much because all of these are actually types of hydrogen bonds. Okay, like this is actually a very strong chemical. So like, I mean, strong molecule. So like this, and this. Like nitrogen is like, no way, I'm not giving away these 3 hydrogens. In fact, it loves hydrogen bonds so much that you see these 2 right here, these valence, I mean these lone pairs. It's like, I can give away one of these and get another one of these really nice hydrogen bonds. And that's actually what it does. So hydrogen is coming in, okay, and it has 1 electron. So in a sense, you need to get rid of one of the electrons and bring the hydrogen over, and that forms NH4 plus. And the reason why I say is like this is just theoretical, because exactly like you would think nitrogen, and they always say it's just one of those exception cases, because nitrogen has 3 hydrogens, couldn't it give away one of them, right? But hydrogen bonds, so when hydrogen bonds with oxygen, nitrogen, or I believe it was fluorine, those 3 there, those are very, very strong bonds that it doesn't want to get rid of. So when nitrogen is already like that, you have a hard time convincing it to give it away. In fact, the only reason why it goes from ammonium back to ammonia is because now it's kind of in an unstable form. You like to always go for neutrality. So that's why it actually is able to accept and get rid of that type of hydrogen, because it's kind of like, well, it's balancing between being a positive charge or a neutral charge. But every other hydrogen there is there to stay. Like that is not moving. So with that being said, that whole, I guess background story, let's see what it's doing here. As we paint this whole picture, it's accepting a hydrogen in order to become, I guess, more acidic. So when the base accepts a hydrogen, or aka a proton, 'cause that's what it really is once it gets rid of the electron. When you're accepting protons, you are defined as a Bronsted-Lowry base. Okay? And with that being said, NH3 is a base because it's accepting, it's receiving a proton, a hydrogen ion. So that whole background was to show that exactly these 3 hydrogens are not for sale. Nitrogen is not getting rid of them. You will not see NH2 minus or something like that, because that's now just, it has so much not working for it. It's now lost already one of its powerful hydrogen bonds, and now it's also unstable. Like you've lost both sides. You're now unstable and don't have that hydrogen spot. While for ammonium, at least you gained a hydrogen even though you now have a charge. So exactly, that's the influence of hydrogen bonds really. So exactly, they wrote it like that, which is completely fine as well. Point being is that it makes it the base, because what this formula is saying is that it's taking a hydrogen, a proton, from water to form that acid. So NH3 is a Bronsted-Lowry base. Water in this case is the acid because it's giving away its proton, and it forms now the conjugate acid ammonium and hydroxide, which is the conjugate base of water. Okay, so with that, this is correct. So now let's move on to question 18. Ooh. What is the structure of isopropyl alcohol? Luckily, you can't see the whole answer there, but you should be able to maybe get a hint for those that are at this level. What is the structure of isopropyl alcohol? Okay, so with that, we need to first understand what iso means when you're dealing with molecules. Okay, so actually, as an example, I'm actually going to write down isobutane. But before, we need to understand what butane is. Okay, so butane looks like this typically. Okay, so there's a carbon here with hydrogens, carbon, carbon, carbon. Isobutane is a specific thing that actually happens specifically to when you have 4 constituents, right? To where instead of it being a straight line, one of them actually comes to the middle. It's called iso because instead of it saying like, if you remember the whole counting, the 1, 2, 3, instead of it saying 2-methylpropane, something like that, we just say isobutane because this is still technically 4. Let me do a different color actually. This is still technically 4 constituent parts, right? It just now is made in like a T shape. Okay, that is what the iso does, specifically the things that have 4 parts. Why do I mention that? Because when you think of propanol, okay, you're thinking, wait, but propane has only 3, right? But propanol, okay, it has 1, 2, and then there's actually a 4th, OH, the alcohol part. Okay, and we circle it 1, 2, 3, 4. So you can actually use the same method here to reorganize this. And what we do get as the answer, let me draw actually in green, because all the constituents are still there, and you have now 1, whoops, thought I changed it to green, 1, 2, 3, 4. This, oops, it's actually a different color, but I've run out of colors, so I'm gonna highlight it instead. And this is the structure of isopropyl alcohol, because iso, especially when you're dealing with 4, I know it can apply to other things, but just remember when you're dealing with something that has 4 constituents, okay, it just means that instead of coming out from one end, it's coming from the middle. Okay, hence how you form that T shape. Well, that's not really, yeah, that's a T. Okay, but yeah, exactly. So that is how you would do that. And interesting enough, it doesn't matter how you orient it, you'll always have that, because whether you make this your main branch, exactly, like you still have this sticking out. So the point being is that this is what isopropyl alcohol is, and it doesn't need any like the numbering thing that we usually do, because everything is configured in a similar way. But yeah, so with that, this is correct. So with that, let's move on to question 19. What is the molar mass of magnesium? Okay, now for those that are watching this, you're probably thinking like, there's definitely a lot of variation of the toughness of the question, because we're definitely using concepts from other questions to help solve other ones. Like for example, knowing how to solve this will definitely help you how to solve things like, you know, find the amount of the grams of what was it again, conjugate base that you needed from that question, like the sodium acetate. So these are just like the basic founding blocks, and although I say basic, they're crucially important in understanding, because you don't want to be making mistakes, especially in chemistry, at your base, because you will get everything above that incorrect. Okay, so now with that being said, magnesium, let's move to the periodic table. Let's list what we know real quick. It is a metal. Okay, and metals, even though typically, you know, when they pair with to form ionic compounds, then they prefer to give away their electrons, but metal in nature show up as themselves. Okay, no change. Usually typically solids. They don't, even though they have these valence electrons with them, they just show up as themselves in nature. No double bonds, nothing like that. Okay, so because it shows up as itself, you probably guessed it, you can actually just read out the atomic mass, and that would be your molar mass. So when you look at that, it would be 24.305. okay, and that would actually be your sorry, give me a second, and that would actually be your molar mass. And with that being said, sorry about that, let me just make sure I'm doing this right. 24.05 grams per mole is your molar mass. Okay, and now let's see here to make sure if we miss anything. Does not look like it. Give me a quick second here. Let me see here. I believe that's everything we need, and exactly we're checking with the question. That is all we need there, because magnesium shows up in nature by itself. And now let me just do this. With that, this is question 19 is done. Move to question 20. So this is correct. Alright, that's correct. Let's move on. So we're approaching the 2-hour mark of hopefully this session of 3. So, because that way we can definitely get a lot of practice in every question we get. So now they're asking, conveniently actually, what is a molar mass of magnesium chloride in grams per mole? So, molar mass of MgCl2. Now, with that being said, okay, we have 1 magnesium and 2 chloride. So, with that, let's see here. Let's go back to our periodic table. Okay, we look at where we have magnesium 24.305 and chlorine, okay, sneaky fella, 35.45. okay, so let's see what we get. 305 and 35.45 times 2, 70.90 plus 24.305, we get 95.205. okay, now let's rewrite that because we want more space to be able to add the important thing that they said. They wanted it in the units grams per mole. So this right here actually would be the molar mass of magnesium chloride. Okay, so let's see here, just to make sure that everything I did was hopefully correct. And exactly, they had slightly varying numbers. Their chlorine was 35.453. So as long as the numbers are close, because periodic table does influence the number you get. So with that being said, it's very important that as you're doing this, you have to make sure that whatever periodic table you're given, that's the one you refer to calculate molar mass. Okay, so this is correct. Oops, I don't even know. There we go. And now we've answered these 20 questions, and we're going to keep on going for tonight. Let's see, question 21. What is a formula for aluminum oxide? So this actually needs to refer to our periodic table. Formula for aluminum oxide. So let me just quickly take a quick water break. So aluminum oxide, we have aluminum and oxygen. So with this, you can either use either form. This is just a convenient way for me to help you review the whole electron configuration. So aluminum, okay, is gonna be starting at neon, and it's gonna be the third row, so 3s2 3p1. Okay, that's aluminum. So in total that's 3 valence. Okay, oxygen, okay. Oh, whoops, that's not correct. Oh, okay, starts with helium, and we have 2s2 2p4. Add these together. Okay, let me actually highlight. Sorry about that. 2 and 1, 2 and 4. Okay, and we get 6 valence. Okay, so oxygen has 6. Okay, and aluminum has 3. So for aluminum to be like a noble gas, would it be easier to go up to 8 or down to 0? It would be easier for aluminum to go down to 0, so it wants to get rid of these, so it needs to go 3+. Oxygen would have an easier time definitely adding 2 rather than getting rid of 6, so it'll be 2-. Now you're probably wondering, how come when I say getting rid of we have a plus? Because electrons are negatively charged, so you want to have the opposite sign. So oxygen, that's why it's 2-, because it's gaining 2 electrons. Now how do we balance this out? The common value between aluminum and oxygen is 6, so we need times 2 and times 3 to be able to get the same amount of electrons being gained and lost. Okay, so knowing that we have now 2 aluminum needed based on this, and because of that we know that we need 3 oxygen. So the formula for aluminum oxide is going to be Al2O3. That is a formula for aluminum oxide. You could also do this by just seeing what row it's on. Aluminum was on the 13th column. 13th column meaning 3 valence, and 16th column meaning 6 valence, but you still end up with this part right here. That part would pretty much stay the same. I just want to do electron configuration just because it's good practice, just for you to really familiarize yourself with it. Okay, so now we have that complete. Let's see what they did. Yep, they say that 3A, well it's actually 13, and 6A, well 16 minus 2. You have to balance it out, so exactly they do the same thing, and Al2O3. So that is what they get. So this is correct. Also, we have question 22. What is the unit for molar mass. Okay, so let's refer to the periodic table, and we've been doing it quite a bit already, but just to make sure we understand it, right? The atomic mass that you see there, right? Okay, atomic mass is a mass for 1 mole of element. Okay, so another way to phrase that actually is that it's going to be the atomic mass, okay, per mole of element. Okay, mass per mole. And you know, per, okay, is like, for example, like a distance per time or distance over time. This pretty much means that there's going to be a division. Okay, so, and we know that the mass, everything that's on the periodic table comes in grams, right? So really what we have is grams per mole, and as we said, per will be a division, so it's going to be G over mole. Okay, and this is the unit for molar mass. Okay, because it's based on even the periodic table. All the numbers listed there are the atomic mass, and that is the mass given per 1 mole of that element. So that's pretty much how we get the unit for molar mass. Yeah. So this is correct. Typically, exactly, like they are correct, that is usually mass is usually expressed in kilograms, but on the periodic table, the atomic mass there is expressed in grams. Okay, so yeah. Let me just see if I expand. Can I expand this? It does not look like it. Okay, that's fine. But yeah, exactly. This is still correct. And now let's look at question 23. Making good progress here. What is a molar mass of CaCl2? So, molar mass of CaCl2. Okay, so back to what we were doing before. Write down your constituents. How many calciums we have, and how many chlorines we have. Okay, calcium we have 1. Chlorine is at 2. So now that we know the constituents, we multiply that by its molar mass, okay, or atomic mass from the periodic table. Calcium is 40.078, okay, and chlorine, all right, is 35.45, okay, and that is equal to 70.90. As you can see, I've started to get used to these numbers. So 40.078 plus 70.90. So the molar mass would be this. To write a little bit cleaner, 8 grams per mole. Always keep the units, because remember, you are adding all the grams together, and it's still 1 mole, because although you see multiples here, right, the mole, right, is referring to the moles of the molecule, and the moles of the molecule is going to be the whole molecule, no matter how big, just as long as you don't have a duplicate of it. For example, if you had 2CaCl2, you just kind of ignore that to get the molar mass, okay? Because you only want the singular form to get the molar mass. The prefix number, that one you can ignore, but any one that serves like the suffix or the under subscript, that one you need to include when you're calculating molar mass. You'll see when the prefix comes in. It's kind of like when you're trying to balance equations. That's when the prefix number comes in handy. So this is correct. Oops, sorry. Okay, just checking over it. They went through everything we did. Multiply that by 2, 1, and exactly got a number that's close to ours. And now it's question 24. Okay. What is the lowest structure of hydrogen chloride? Oops. There we go. So now, I know you've probably seen the answer by now, but let's pretend like we didn't see that. Okay? So, hydrogen chloride, okay? We want the lowest structure of that, okay? And now, we first need to find out, based on the periodic table, how many valence electrons it has. So, you probably guessed it by now. More practice of writing the electron configuration. Hydrogen is just 1s1, okay? And chloride, okay? If we refer to here chlorine, neon, okay? So that's hydrogen, okay? Chlorine. Alright. We have starting at neon. Okay? And it's going to be 3s2, 3p5. Remember, we add these together and we have 7. So 7 valence electrons and 1 valence electron. So you can kind of put it together that in total is going to be 8. Okay, so it'll be hydrogen and chlorine. I'm going to have chlorine that has 5, 6, 7, and hydrogen that has 1. So right there, because it still adds up, 1 plus 7. Okay, you have 8 in total for the electrons you should be counting. Okay, and exactly, that's exactly what we hear. So we have here, so this will be the lowest structure for hydrogen chloride, which by the way is a strong acid. Okay, so there we go for question 24. Let's see here. Yep, they just have a bond there instead. Exactly, we have 3 lone pairs like they do. I still do recommend that when you're doing this, you want to make sure that your bonds are written as electrons, okay? And 2 electrons is a single bond. A double bond would have 4 electrons and etc. Okay, this is correct. Just checking over the work to make sure we didn't miss anything crucial. Nope, I believe that's all. Okay, so now let's move on to question 25. Okay. So now this is where questions get real interesting. A 20-gram sample of methyl alcohol. Okay, so let's write down what we know. 20-gram sample of methyl alcohol, CH3OH, instead of methane, which is CH3O4. Okay, and they have the molar mass there. So because they give us the molar mass, that's the molar mass we're going to use. Okay, we're not going to actually find it based on the periodic table, okay, because that would just throw things off. Okay, so molar mass is 32.04 grams per mole. We're going to use what's given to us. Okay, was dissolved in 35.6 grams water. In 35.6 grams of H2O. What is the mole fraction? Okay, so with that being said, we're given quite a bit of data here, right? Okay, now mole fraction, all right, is, maybe you can guess it, but I'm going to explain it. Okay, it's going to be percent of mole of substance. Okay, and that can be found with mole of substance over total moles times 100. Okay, that's how you calculate the molar fraction. Now, with that being said, though, you're probably wondering, how do we get the mole fraction? Because realistically speaking, in fact, I'm actually list on the answers here because it actually gives us a clue on which ones we can cancel out. Okay, so A was 0.316, B was 0.624, C was 0.3360, D was 4.17, E was 0.240, right? So molar fraction is mole substance versus total moles times 100. So the reason why I say we can actually cross something out is because total moles have to be greater than or equal to the moles of substance, as you cannot have more of a substance than the total you have. Like if I had 100 grams or something, I cannot have more than 100 grams of part of it. Now, because we know that, we know it cannot be D. Why? Because D is 4.17, meaning that it completely, in fact, let me actually fix the formula to make it more sense. They're not even doing times 100 to find a percentage. They're actually just getting the fraction itself, okay? Hence why it says fraction. For some reason, I always jump right to finding percentage. But exactly, the fraction, the biggest number it can be is 1, meaning that all of your substance is what makes up the total mass. So having anything greater than 1 is automatically not going to be the answer, okay? So now with that being said, let's go right to actually solving the question. So I'm going to write in red. You're probably wondering, how do we find the total moles? They actually was gracious enough to give us the grams and the grams per mole. So using that same formula, actually, we can actually find the amount of moles for CH3OH. So remember, we want to make sure that whatever we want is at the top. So 1 mole, okay, all right, 32.04 grams, okay, and that would actually equal, because these cancel out, divided by 32.04, 0.624 moles, okay, of CH3OH, okay? That's what we have. But we're not done with the question yet, so don't just go and answer it right away. It was dissolved in 35.6 grams of H2O. So interesting enough, we actually are able to get the moles, how many moles of water that is as well, because the fact that I guess in this one they just assume that you should know, but H2O, we're going to use that same way we've actually been solving the other questions. So H2O has 2 hydrogen, 1 oxygen. Just keep things you know, consistent. All right, 1.00, what was it, 6 or 1.008, okay, and 15.999, okay, 2.016, 15.999, add them together. Okay, 0.016 plus 15.999, 18.015 grams per mole of H2O. So now we have that. Okay, we actually have 30, because we want do the same thing with water. 35.6 grams. 1 mole of water, okay, is 18.015. Okay, so that's 35.6 divided by that equals 1.976 moles of H2O. So now we're given these two numbers, but again, we're not done yet. We need to find the total moles. So total, so N total, okay, is equal to, we need to add these two together, okay, plus these two, 2.60, okay, of water and methyl alcohol. That's what the right name is. Yeah, methyl alcohol. Okay. And now we use this formula we said, mole substance versus total moles. They're asking for the mole fraction of methyl alcohol. Okay. So we want that 0.624 divided by 2.60. So there we go. 0.624 divided by 2.60. Okay, so the mole fraction we get is 0.24 as our mole fraction. No units because it's just a fraction. Okay, it's like a relationship between like exactly the total. So with that being said, this is literally the number we got. So we actually look at the choices, and based on that, the answer is E. Okay. And the reason why I even talked about crossing out these, because sometimes you can work a lot better when you have less options to choose from. Okay. So mole of exact substance over total moles. They found out the moles of the methyl alcohol and water. Then they added together, and yep, 2.40, and they got the answer is E. So this is correct as well. So hopefully that was able to apply a few things together to kind of be able to work your way around this question. And yeah, hopefully your learning tonight has been going well. With that, let's move on to question 26. Oh wow, this is a doozy. What is the electron pair molecular geometry of xenon? Wow. Okay, xenon tetrafluoride. Didn't even know that was even something that's possible. But you remember our best friend sulfur? Well, it turns out sulfur is not the only one that can do that. So with that being said, though, xenon. Okay, let's actually use this time to actually do the the electron configuration, so we can know the valence electrons. So xenon goes like that. Oops. And we want to actually start from krypton. I know we start from noble gases, but when you want to find the electron configuration of a noble gas, you start from the noble gas prior, okay? And that's going to be row 1, 2, 3, 4, 5. So 5s2, okay? And it's going to go through all this, right? So it's going to be 4d10, okay? And then it's going to be 5p6. So we're going to reorganize this, and it's going to be krypton 4d10, 5s2, 5p6. And because exactly these are where the 5s are, you add up those. So now you can say for without a doubt that krypton has 8 valence electrons, okay? And fluoride, we've done it before, but just as a review, okay? Start with helium, okay? Helium, yep. And be 2p, right to the p, 2s2, 2p5, okay? And now we have this, both at 2s, okay? We can say that it has 7 valence, okay? Okay, so with that being said, we have 4 fluorides, so xenon is most likely the one in the middle, okay? So with that being said, okay, we have xenon relaxing here with its whole 8 valence electrons. Now, as I mentioned, just like sulfur, for some reason xenon, even though it's a noble gas and you would think that it can, you know, it would prefer just be like that, for some reason it means that even I can't explain. There's probably is an actual explanation to this, but at my level even I can't explain it. Fluorine comes in and says I'm gonna take 1 of each. So there's 4 fluorines. They come in, drawn a different color actually. They say I don't care how comfortable you are, one of those electrons is mine. So let me actually, so these two form a bond, okay? And then now we need to do that 4 more times. Well, 3 more times, I mean. So bond here, okay? And again, okay? Bond here. It's pretty much saying I do not care. Oops, that's not iron, it's fluorine. So there we go. Fluorine's pretty much here to ruin xenon's day. Okay. So the reason why I drew it like that, although it's quite messy, is because this allows us to actually draw out a cleaner Lewis dot diagram. Okay. So it's gonna be xenon, okay, 2, okay, and yes, you've probably seen it's like, oh yes, and you guessed it, this is going to be its Lewis diagram. I noticed right away that it's not even in exactly, no, it's no longer in its 8 pair mode. It's now formed this octahedral structure, okay? And now, with that being said though, because actually it's like that, here's where I have to review the shapes again. So, but actually let me first give my best shot, because I do believe that this is how you do it. You see how there's a valence valence electron on the top and the bottom, right? When you actually draw it as a molecular structure, it should look like this, okay? So remember how I mentioned like just like the whole box thing? So imagine this like all one plane. So exactly, it's kind of like that, and with the electrons sitting at the top and under it, okay? That's what we have here, okay? And surprisingly, this would still be 90 degrees, okay? Because in fact, I would ask you, is this is xenon tetrafluoride polar or non-polar? And yes, you see valence electrons, but surprisingly, because of how it's oriented, this is actually non-polar. It has nowhere to go. For every pull in one direction, there's an equal pull in the opposite direction. If you want to go up, there is the same lone pair pulling you downwards as well. Any fluoride any direction, there's another fluoride in the opposite direction. So this molecule should actually be non-polar. Now I'm saying that a lot of stuff right now, but if I'm wrong, I'll be quite embarrassed. Let's see here. Yep, that is correct actually. It's exact 90 degrees because, as I mentioned, right, the electrons like to kind of push everything away from it, right? But if you have two lone pairs in both ends, right, it kind of forms a sandwich. A perfect sandwich to where it's not bent anyway, so it still forms that perfect 90-degree angle, as you can see here, making this whole thing actually non-polar. But what is a molecular geometry? I'm quite embarrassed because I literally put the paper away. But the molecular geometry for this would just be, that's actually a great question. Do I have the name for it? No, I do not, unfortunately. We'd have to go back to that question that listed all the molecular geometries out. And I'll probably actually have a page here, actually. Molecular geometries. Yeah, just pull up a chart. These are the things I'm going to start saving just because exactly. Considering these level of questions, we'll have to refer to them quite often. So it's easier to have them. And now let's see what exactly that is. We're on the 6. Exactly, actually, that's actually something I should have mentioned. Because we have 4 bonds and 2 lone pairs, this is going to be 6 4 electron groups. 6 electron groups, okay? And now, for this, it's actually going to be square planar, okay? So I was on something here when I drew a plane. I just didn't know the word for it, so it's actually square planar. I think there should be a better sheet because 6 can keep going to get more and more to get into more choices. So let me see if I can find a better sheet. Oh, that's not it at all. Okay. Molecular geometry. Oh, maybe this one might work. No, I guess it only stops at square planar. Huh. Alright. Let me see here if this one's better. Because I know there was one I referred to that was extremely helpful. Yes, this is what I want. Because it goes further than that. So let's see if we can find out the website. But I'll find this later. I'll just keep that tab open. So yes, they have xenon tetrafluoride. Oh. Did they say what type of thing? They do have the... So, although my Lewis diagram is quite ugly, I do like the way they drew it there. It's a lot better. Okay. Where they have that, still have the... And as I said, I like to draw in terms of actual electrons. Okay. And we have just like the 2 extra ones here, but because you know it's Lewis diagram, it's always going to look a bit messy, but yeah, so it is square planar if we're asking about geometry, but they did get what it looked like, right? So I will say this is still correct. Exactly. And it is an octahedral arrangement, but it's a specific type square planar. Okay. Specific type of molecular geometry is square planar. So with that, we've answered number 26. So let's move on to question 27. If it doesn't load properly, we might have to stop here for tonight, but let's see. Okay, it's loading still. This is a little bit concerning. My plan was to do 30 questions, so I was only 4 questions away from finishing that. I really hope that this loads properly soon. Let's see. Give me a quick second here. Sorry about this. Okay. Good news is that it loaded. So with that, we're back on business. Ooh, and with a quite intense question actually. What is Ka in chemistry? Okay, so you probably already saw the answer there. But do you remember when we were solving for that question where we were discussing finding the amount of conjugate base we needed, the NaCH3, the sodium acetate? So, as I mentioned, actually here, we have a whole list of it. Ka, in fact, we'll actually look at this table here, because this will actually help us visualize in our head what we mean by Ka. So, K, okay, just by itself, is known as the dissociation constant, okay? And that can vary from 0 to, well, yeah, actually, yeah, 0 to infinity, okay? Like, it can get as big as it wants, but it cannot go to the negatives, okay? Because the point of K is how much something dissolves when it's submerged in a liquid, usually water, okay? Because when they talk about the K, it's for aqueous solution, so submerged in water. Now, the reason why I put it like this is because there's two types of, I guess, dissociations that we deal with, okay? We have 0 to 1, okay? And we have 1 to to infinity, okay? Or you can just simply put K greater than 1 if that makes it easier to read. K greater than 1, okay? So these are the two kind of divisions we have, okay? When K is greater than 1, think of salt, NaCl, sodium chloride, okay? You put that in water, bam, all gone. Unless it's supersaturated, all that sodium will dissolve in water, okay? Now let's think of an example of something that doesn't like to dissolve, like calcium. Calcium hydroxide, I think that's one. Point being is that one doesn't dissolve so much, okay? Actually, before we even go into calcium hydroxide, let's talk about NaCl more. Sorry about that, because we said to relate it to how it relates to K. So fully dissolves in water, right? That means the dissociation constant is greater than 1, in the sense that when you put it into a solution, it likes to fully dissociate with each other, and in the sense like with all the competing factors in the solution, it still prefers to be apart. That's typically what dissociation constant greater than 1 means, okay? Now dissociation constant less than 1, now we can talk about like calcium hydroxide, okay? This is what you know as, like precipitate. Like, when you mix two solutions together and you form precipitate, that's because their dissociation constant is extremely small. Like I said, you can never go into the negatives, but it prefers to be together than apart. Once you're less than 1 for dissociation constant, it means that you prefer, in as many situations as possible, to be together than apart, okay? So, with that being said, as you probably noticed, they said A, Ka, not just K. That is simply everything we said here, but applies specifically to acids, okay? If you have, so Ka is for acids. Okay. Now, as you probably are thinking, right, kind of like NaCl. If you had hydrogen chloride, or HCl, so hydrochloric acid, right? Kind of like salt. Okay, put that in a solution, that thing will completely dissolve. It likes to be apart. That's because its Ka value is much greater than 1, making it, as you probably guessed, from discussions before, a strong acid. That is actually where they get the whole terminology of strong acids and weak acids from, because when your Ka is greater than 1, in fact, as you see here on this list, you become a strong acid, okay? Because here the Ka is now 1, right, for hydronium ions. But you see nitric acid, sulfuric acid, hydrochloric acid, chloric acid, these are all strong acids because your Ka value is greater than 1, meaning that you put that in a solution, you put that in liquid, bam, you actually have the hydrogen ion and its conjugate base or something like that. Point being is they will not go together in the water. Now, weak acids is when the Ka is less than 1, but still greater than 0. Because like I said, 0 means that it just won't dissociate. And for most things, it's really hard to have a dissociation constant of 0. But the smaller it is, the least likely you're going to see it actually separate. So, as you know, let's go to the actual weakest one here on this list. Water. You're most likely just going to see exactly like, it's a good example. H2O, you're not going to see H plus and OH minus so freely. Although, as it even indicates here, 1 times 10 to the negative 14, there's a small amount in the water of H plus and OH minus, but it's almost insignificant because of how small that number is. That means like literally for every 1 of H2O, there's 1 times 10 to the negative 14 of the dissociations produced. So that's an example of, like, you could technically say yes, water is the weakest of acids, but exactly, like, it gets really convoluted when you start thinking like that. But point being is that yes, Ka, that's actually used to determine whether it's a strong or weak acid, and you can also have Kb as well, but that's literally just for bases. Still the same dissociation and everything. But now, something I like to point out actually is that, so sulfuric acid, right, is considered a strong acid. And I'll write this down actually, because H2SO4, okay, is considered a strong acid because it likes to now break down to the H plus and SO4, H plus and HSO4 minus, okay? The reason why I wrote it like that is because acids and bases can only gain and lose electrons 1 at a time, okay? So it doesn't just do like a whole skip to where now you have 2 H's roaming about and 0 H's on the SO4. This is what it would form, right? This is a strong acid, so you put that in liquid, okay? It goes straight to that, okay? Now we actually have, okay, this in there, HSO4, which is, I think, is per sulfuric acid, like that. Let me see actually. But point being is that HSO4 is actually a weak acid, so that actually dissociates as well. Okay, so let's find it. I can find it here. HSO4. There we go. Sulfurous acid. There it is, right here. Okay, it's a fairly weak acid actually. But the point being is that this also dissociates. Okay, and the reason why we put this is because now that it's less than 1, it can go either way. It can go back to forming the HSO4 or break down to H plus and SO4 2 minus. Okay, so the reason why I'm saying this is because, simply put, is that you have one strong acid, but it actually produces components that are also considered weak acid as well, which is all determined by that Ka value. Okay, so in summary, what is Ka in chemistry? K is only dissociation constant. Ka is the dissociation constant for acids, and specifically it can tell you whether it's a strong or a weak acid. If you see a Ka value less than 1, so 1 times 10 to the negative anything, that is going to be a weak acid. If you see it greater than 1, that is a strong acid. Okay. Alright, and exactly, they mentioned it, which is good, that this is all dissociation in water. So you don't want like a solution of like ethanol or anything. This is water as the aqueous, solvent, like the solution that's in. Okay, so this is correct. So now that we've finished question 27, we're going to go over to question 28. Okay. The relative molecular mass of methane is CH4. So relative. And this is key because this is not just something we just go straight to our periodic table. It's trying to establish similarities, okay? So for this one, we're actually not going to use periodic table because the goal here is when they say relatives, they want you to use the information they provide in the question. Mass of CH4 is 16.043 grams per mole, okay? And now they want to know the relative mass of ethane, okay, which is C2H6. And now they tell you that for here, carbon is equal to 12.011. The reason why I keep stressing relative is because they don't want you to go to your periodic table. They want you to use the information they gave you in this question to find out what the relative mass of ethane would be. So with this, right, they gave you the amount of carbons because they want you to figure out how much each hydrogen actually weighs. Okay, because exactly, we have 1 carbon and 4 hydrogens, okay, and we know now carbon is 12.011, but 4 hydrogen is equal to 4x, okay, so that's 12.011 plus 4x is equal to 16.043. This is how you can solve the question, okay? You're not going to refer to the periodic table because I can guarantee you if a question like this is asked, they're going to be really stingy about what answer you get because they want you to use not just the numbers you got from the table, but the relative numbers based on the question here. So here, you solve for x. So 12.011 plus 4x is equal to 16.043. So that's 4x is equal to 16.043 minus 12.011, and then we divide all that by 4. So now let's see. So 16.043 minus 12.011 divided by 4. So x is equal to 1.008. So this is the relative grams per mole, so the molecular mass of hydrogen, okay? And now because we know that, we can actually solve for ethane now. Ethane is C2H6, okay? So now we have 2C 6H, okay, times 12.011 and 6H we have based on this that we got by solving the relative values, 1.008. So we solve that, okay, and 12.011 times 2, 24.022, and 6 times 1.008, 6.048, okay, and we add those two together, 30.07. So the answer is 30.07 grams per mole, okay, of just to make sure I did everything right. For the ethane, this question, you should not solve a periodic table. I'll say it again because they're going to be really stingy of what value you actually get, because we use the periodic table. Most of the time you'll be close, but you most likely will not be correct. So this one, funny enough, they seem to have just gotten the number straight from like the periodic table, and coincidentally actually that 1.008 is actually the value here for this periodic table. So realistically speaking, they are correct, but I'm going to emphasize that they got lucky. So this is correct, but you want to use the values given since it's relative. So yeah, relative is a key word. So chemistry questions, you can kind of see them as well as like English comprehension. Don't miss out on information given to you from the question, because that's very crucial. Okay, so now with that, let's go on to question 29. Oh, I think you spelled correct wrong. Can I fix it in time? Correct. Hopefully this will help it move on to question 29. Oh, there we go. Okay, good. Hopefully I got my first one, because I'm not spelling correct right. It's kind of embarrassing. Okay. So let's see here. If it does freeze at this point, we might just call it night here. If not, then we're actually good to move on. Okay, let's wait a little bit longer. This can't be good. Oh, on the last two questions too. Oh, well. Let's give it let's give 1 more minute. I'll give 1 more minute to load. I'll be right back. So that way, like, hopefully by the time I get back it does load. Oh, perfect actually. Okay, so what is the electron configuration of chromium? This is amazing, because we've actually done this. I knew it looks familiar. So, chromium, right? What is the electron configuration of chromium? So, now let's actually do this question. Chromium, right? Okay, we have Cr. Okay, so with that, we already have a great start. That's the whole question. I'm kidding. We want to start with, we can either do a shorthand or longhand. We're actually going to do the shorthand, then we're going to actually we're going to do a longhand first, okay? Because we want to make sure that at least we see that once, okay? Chromium is on the 4th row, okay? So with that being said, we gotta start from the beginning. So 1s2. That is a completion of the first row, okay? Then we keep going. 2s2, 2p6. That's the second row done. 3s2, 3p6. That's the third row done. Now 4s2, 3d4. Okay. Now I don't know if you recall what happened earlier, but I'm actually going to go through this again. So for now, I'm actually going to write the short and long version. So the short version is, instead of it being all the way to the 3, we have argon. Okay. And we're going to reorganize this actually. So we're going to actually move this here real quick. And we're going to move this, oops. We're going to move this down because we want the 3s to come before the 4s, okay? Now, 3d4, 4s2. if you think that we're done here, okay, you're horribly mistaken. All right, he's now actually going to do the notation, the I guess atomic notation. I forget what the name is called, but pretty much where the electrons are actually pointed in terms of like their positive or negative spin. Okay. The reason why is because it actually help us figure out how to actually draw this chromium correctly. Okay. For this one, we're actually only going to do the shorthand. Okay. All right. Actually, let me do it in red. You know what? Let me just be right back. I wish there was a way to pause it, but I just got to grab something real quick. Okay. Okay, sorry about that interruption. We're just going to get right back to it. So with that being said, we actually write the notation for it, right? Remember how we need the D row first, 4, 5, and then we have the S, okay? So we have 3D, 3D, and 4S, okay? So based on this, right, we actually have this currently, okay, 1 up, 1 down, okay, and then we have 4. Now remember what I said in terms of the whole reorganization. This actually applies here specifically because if you recall, D and S or P levels, so D and S levels in this case, are enough of a energy difference to where certain elements like to reorganize themselves so that way they can more comfortably fit. So with that being said, instead of being like that, we're actually going to have this, because that way you can have at least 1 electron in each D shell, okay? Well, yeah, exactly, in each D shell, because now each D shell is filled and the 4S shell is still filled. So with that being said, like this, right, this is no longer going to be how we wrote it. We're actually going to make the changes accordingly, okay? Because now we have 3D 5 4S 1, okay? This is going to be how you write it, and the only way we can actually figure that out was because of actually our notation, okay? Which is why notation is quite important. And exactly this, I do believe that earlier I did do exactly this as an example, and I think I got it from here when I was reviewing the questions actually. But the point being is that electronic configuration is 3ds 4s1, 3d5 4s1, because of this. Actually, you see all these filled d orbitals, this is actually more stable than having 4 of the 5 filled and 2 in the s. Exactly. So like I said, the s and the d orbital are different enough in regards to their energy levels to where this is considered the more stable version for chromium. Okay, so with that, yeah, this is all we have for this question. So now if somebody asks you what is the, I guess, valence electrons for chromium, yeah, you could technically say that it would be 1, because well, that's a whole different thing, because transition metals, that's what I mean, that they act very strange. You can never really tell what they're going to do, unfortunately, when it comes to like bonding. It could have 2 or 6, which is the valence electrons. We can't really figure it out, to be honest. I know one of the things that are common is like chromate, Cr2O7, but in what context and how it actually forms, honestly, I could not tell you, unfortunately. But yeah, so that's just a fun little side note that chromium is just a very strange element. Okay, now let's go with question 30. Hopefully, it's loading a lot faster. Nice. This is a very nice, straightforward question to end the night with. What is the molar mass of NaCl? Okay, so with that being said, okay, let's actually get our constituents. Okay, we have 1 for the Na and 1 for the Cl. Okay, so there's luckily not much math for us to do. Ooh, you can tell that I'm getting a little burnt out, because even this question is giving me issue. But exactly, we get the atomic mass for sodium right off the periodic table. Okay, and then we get the atomic mass of the chlorine. Okay, and this is not perfect, so we have 22.990 times 1. Don't know why I had to put that in my calculator. It's going to equal itself. Okay, then we add these together. Okay, that's what I needed my calculator for. 58.44 grams per mole. And to write it cleaner, the molar mass of sodium chloride. Okay, this is what we get. And straight from that, the reason why is just because you have 1 of each constituent, so you add their atomic masses together, and that's your molar mass. So exactly, like this says, it's kind of giving you a breakdown. It's computed using the periodic table by adding the molar masses of the individual atoms or elements. Okay, silver chloride. I'm pretty sure they meant sodium. Okay, because they say NaCl later, so that means sodium chloride. Okay, I had to just double check that it was actually sodium and not silver. So so for every mole of sodium chloride is 1 mole of sodium and 1 mole of chlorine. And so you just multiply like that, add it together, and with that you get 58.44. So with that, this is also correct. So with that, let me click this is correct. And with that, I just want to thank you again for joining me on this stream. It was definitely a journey. I had a lot of fun answering these questions. And hopefully, because of how we try to keep consistency, some things that were really hammered in home today in terms of calculating the molar mass and also noting the electron configuration. Those are probably the 2 biggest topics I covered tonight. Other than that, though, if you have any other questions, you can definitely feel free to reach out to the links below if you ever need more tutoring or just homework help in general, okay? So with that, I just want to thank you again for joining me tonight, and have a wonderful rest of your night.